You may have seen the null value in many languages. Most of the times when we see null, we are thinking about an absence of a value. In functional programming, we don't have the null value similar to what you've seen traditionally. In this video, I'll explain how we can model these scenarios. But first, let's see what is wrong with the null value. In order to do that, let's consider two functions, one partial and the other total. Here, divide2 function is partial and increment is total. As you remember from previous videos, total functions map every possible input to an output, and a partial function is a function that at least for one value in the input side, there is no output. Here, divide2 function is not defined over value 0, so it's partial. I mentioned that all functions in functional programming should be total. So in order to make divide2 total, let's return something indicating output is not available for input 0. The first thing comes to mind is null. That is why it exists, right? But if our language accepts null for floating points, then we have some challenges to compose divide2 and increment. Let's say the author of increment is not the same person who defined the divide2. It means that author of increment needs to consider the null value for input because it's part of its input set. Although that the sole purpose of increment is to only increment numbers, because of the language technical challenges here, it also needs to consider null in its implementation as well. More generally, for any operation in these programming languages, you need to consider null too. And now that we add the null mapping in the increment function, it is safe to compose divide2 and increment. You may ask what's wrong with that? Whoever developing increment should be responsible to implement it correctly. My answer would be, are you yourself always as responsible as you should when you're coding? Missing considering the null value can lead to an unexpected behavior, and there is a chance you may mistakenly make that error. The compiler or interpreter is not helping you here, because null can be passed for many different types, and other engineers may build on top of your bug and create more bugs themselves. Mishandling null value is known to be one of the most popular bugs in programming. That's why the inventor of the null calls it a $1 billion mistake. Okay, so now we learned our lesson. Null is bad. What should we do now? What is the right way to handle this? But to be honest, null doesn't have any problem by itself. We need to name our concept of quote-unquote absence of a value something. Then why not naming it null? Maybe a better question is, why we are letting our values to be null when we literally type them, for example, integer? Let's remind ourselves again, what is a type? Type is simply a set of values. For example, integer type is a set of all integer values and nothing else. Frankly, the issue is the way languages are handling null. We need to exclude null from our types unless we explicitly say they have the null value. Let's name the type that has all the integer values plus the null value. Let's name this type maybe integer, because a value from this type can be any integer value or null. Integer and maybe integer are two different types, but they are only slightly different. One just has one null value more than the other. Or in other words, cardinality of the type maybe integer is the cardinality of the integer type plus 1. Cardinality of a type is the number of values exist inside that type, and it is shown with two pipe symbols around the type name. Let's try to define maybe integer type using the integer type. Assuming integer is actually a type in TypeScript, we can define maybe integer like this. This is handy for quick typing, but can we abstract this to any type rather than only integers? When we say any type, we should immediately think of generics and type constructors. Let's define our type constructor option, which receives a type and returns a type that null is added to it. So now we can use our option type constructor to define the maybe integer. Because of some edge cases, we need to do a bit extra rather than just adding the null to our input type. Just to talk a bit about the edge cases here, think about passing maybe integer to the option. Since maybe integer already has the null value in its set, adding null again doesn't add anything new to the set. So the new type is again maybe integer. We sometimes want to differentiate those null cases structurally. Let's fix this. By defining type constructor sum, now if we pass maybe integer to the option, we receive a different type than maybe integer. For the null value, just to follow the practices in books and well-known functional languages, let's define a new type none, which only has one value in it. To be honest, if our language uses the null value correctly, like TypeScript with some tweaks, null would work just fine and we don't need to define none. We will define none with a small letter n in just a second. The other popular names for option, sum, and none are maybe, just, and nothing. Let's create a helper function to create an instance of a sum type and define none value in a small case. As you see, none value is a singleton value representing the absence of a value. Symbol is a feature in JavaScript ES6 that creates a unique object throughout the application. So when you create a symbol, there are no other values equal to that, and it's unique in the whole application. Something to note here is you don't have to use symbol for none. As a matter of fact, functional programming doesn't talk about how you should implement sum and none internally. Let's look at another way of implementing these two. Here I'm using objects to represent both sum and none values. As you see again, none object is treated as a singleton value and sum object wraps a value. This is actually the way FBTS is implemented these types. FBTS is one of the most well-known libraries for functional programming in TypeScript. I'll put a link to this library in the video description. Going back to our first example, when we were careless and null was implicitly part of the number type, we could compose divide to and increment. But we know that in case of an input 0, our compose function behaves unexpectedly. Let's rewrite divide2 to return an option. But now we have a new problem. The output type of the divide2 is not matching the input type of increment. Then how can we compose divide2 and increment? The good news is there is a clean and beautiful way to do this, but we are not there yet. We will look into it when we get into functors. But for the sake of this example, let's solve this by a custom lambda function. So our compose chop bump function first tries to divide 2 by the input. If dividing fails, it returns none. Otherwise, it increments the divided output. The isNone function is a custom type card to check if the type of x is none or not. We will look more into it in the demo video. Alright. Thank you for watching this video. Please like and subscribe, and I will see you in the next one.